Hello everyone, I'm Tushar Khod and today I'll be presenting our work on learning to communicate with agents. This work was done in collaboration with my colleagues at AI2. In this work we asked the question, can current AI systems learn to talk with agents to solve more complex tasks? And while they're unable to do so yet, we hope that our proposed dataset can help develop better solutions for this problem. So first, what do I mean by solving a task by talking with agents? Let's consider the following scenario. Say someone mentioned a popular book series about a kid with a lightning scar that you should read. You don't remember the name anymore, but you'd like to buy those books. So the first thing you might do is ask your Google Assistant which book series has such a kid, and then get the list of books in these series, and now you may use your Alexa assistant to buy each book for you. Basically, you are able to solve a multi-step task by decomposing it into simpler subtasks that you know can be solved using existing agents. You interacted with these agents in their natural language without ever relying on any agent internals such as their training data or knowledge bases. So the question in this work is, can you build AI systems to also do the same task? We formalize this as a task of learning to talk to agents. A natural question here might be, why should we build such AI systems? First, by using existing agents, we can reuse the skills of our expensively trained models rather than waste computations on learning them again. We can even use black box proprietary models behind APIs in this framework. Additionally, as the task gets more complex, requiring composition of more and more skills, composing existing agents is a better long-term bet than learning a new monolithic model each time. The resulting systems are also naturally modular and interpretable through the communications with the agents. And at a technical level, this poses an interesting research problem of searching for solutions by communicating in free language with AI agents. And so how can we build systems for this task? Unfortunately, current datasets lack sufficiently accurate composable agents, resulting in uncontrollable sources of error, or have shortcuts exploitable by black box models, negating the need for such skill composition. So we built the first dataset designed for this task, CommaQA. CommaQA is a synthetic multi-hop QA dataset guaranteed to be solvable using our agents. It is challenging for current black box models as well as task baselines. Next, I'll go into more details of the task and the dataset. To define the task, let's consider the following scenario with three agents: a Google search, image search, and a visual question answering or VQA model, and the list of questions that you can ask these agents. Now say you're trying to remember which Harry Potter book had a car on its cover. Just based on the sample inputs, you know how to get the list of books in this series from Google, then get the book covers for each book in the series using image search, and identify which book covers have cars using VQA. You can then filter down to the one book where the VQA answer was yes as your final answer. Basically, you were able to answer this question using just the three agents and some examples of their valid inputs. Additionally, to be able to train a system for this task, we assume access to the complex task training data too. And what we would like to do given these inputs is to build a system that can learn to use the agents in a similar manner as shown before. Note that unlike standard QA datasets, the system has to communicate with the agents to answer these questions. For generality of the task, what we assume to not have access to is the training data of the agents. First, the agents might have been trained on millions of examples and retraining on them would be wasteful. And in cases of Google and Alexa, we don't even have access to their training data. Secondly, the agent's internal knowledge is also often not available or hard to materialize when saved within the model parameters. And finally, the complex task may only have label supervision and no supervision on valid conversations with the agents. This is more of an issue of annotation costs and less about the infeasibility of updating such annotations. Given this new task, we developed a new synthetic dataset, CommaQA, to enable progress on this task. CommaQA is posed as a multi-hub QA dataset, with each agent as a single hub QA model. We have three different styles of questions inspired by prior datasets that form three different sub-datasets. CommaQA-E, where the solution approach is explicitly described in the question. For example, what awards have the actors of Oscar-winning movies received? The model here still has to figure out how to communicate with the agents and which agents have the answer. The other two datasets are CommaQA-R, where the solution approach is implicit in the question, and CommaQA-N, that requires numeric reasoning. Note that while inspired by reading comprehension or open domain QA datasets, CommaQA is a dataset for learning to talk to agents with no reading comprehension context or corpora. The resulting CommaQA dataset has certain key properties. We avoid any conflicts with world knowledge by using novel made-up nouns. We ensure that the system needs to interact with the agents to find the right solution strategy by varying the agents that can answer a sub-question. For example, the awards won by a person might be answerable by a text QA or a table QA agent. Since complex questions often require reasoning over lists or dictionaries, as we showed in our example, our dataset is also designed to require reasoning over such structures. We additionally introduce new operators that can execute natural language questions over such structures. Finally, to ensure rapid experimentation, we implement agents as fast and accurate symbolic Python functions. We provide auxiliary data such as the knowledge base and conversation supervision, both as stepping stones and for oracle upper bounds. In terms of results, we show that current task baselines are unable to solve the task, even though the upper bound for such methods is 100% when trained on the conversation supervision. However, black box models, even in the oracle setting of having all the agent's knowledge, find this task to be challenging. Beyond this IID setting, we also provide a compositional generalization test split that's described in the paper. In conclusion, in this work we present the task of learning to talk to agents as a better way to build models for new complex tasks. We provide a new synthetic dataset, CommaQA, that can allow researchers to focus on this extremely challenging problem without confounding issues. And finally, we hope that the community works on developing new methods for this task, for example using question semantics and rewards. Please come to our poster or refer to our paper and code at the link below. And if you have any questions, please feel free to reach out to us. Thank you.